5 or 6 lessons ago, we talked about leaves, right? Remember, we want to find out.
You said you were gonna do that breakfast lesson or something, but you forgot.
Yeah, okay. So last week not last week. I mean, last lesson we talked about not last lesson actually. So on that day,
a few lessons ago.
Yeah, a few lessons ago we talked about this problem, and we want to find out. We want to count how many paths from the root to the leaves. You know, each node is from 1 to 9, one single digit, and we want to find out how many paths can be formed as the palindrome, right? So, for example, like 233, the 3 digit 233 can be used to make a palindrome, 323, and 211 also fine. We talk about the depth first search. The key thing to solve this problem is recursion, depth first search. So how do we find out the values we collected from the root to the path? We use the numbers, those digits. How do we check if we can form a palindrome path?
If it's an even number, then there has to be even number
Of digits.
like, for example, there have to be an even number of quantity.
Even number of quantities, yes.
Yeah, like there'll be it could be like 2 2s or 4 6 or something like that.
But can we have an odd number of quantities?
No.
Why not? Look, 233.
No, I said even in an even number.
What do you mean even number?
In an even number with even numbers. Those are 3.
Yeah, but we can
3
use.
is an even number. Yeah, I'm saying.
Okay.
For an odd number,
Okay.
it's the same as even number, apart from one of them has to have an odd number of quantities.
Okay. So can you summarize these two, just to make both cases into one? So if it's odd number, then we can only have one, at most one, odd quantity. For even number, we need all the elements to be even quantities, right? Okay, so in both cases we can say at most we can only have at most one element which is odd quantity. The idea is that we count the number of elements and the frequency, and then we can only have at most one element which is odd quantity. Depth first search, right? Depth first search. We actually talk about 2 solutions. One is using the array to store these frequencies for each digit, and actually we don't really need to count how many frequencies each number appears. We just need to know whether it is odd or even. So we talk about this exclusive OR. Do you still remember what's exclusive OR?
Ta-da!
What's exclusive OR? Do you still remember?
It means no two can be the same. No two can be the same.
Okay.
The first one is 0. That's 1.
Okay, so 0.
0 1 1 0.
Yeah. Okay. So if it's different, it's 1. Otherwise, it's 0. Okay. So why can we use the exclusive OR? So for example, like 1 exclusive 1, that becomes 0. 0 exclusive 1 becomes 1. Okay, so you see, if we do the exclusive OR, you make the opposite. 1 becomes 0, 0 becomes 1. Okay, so that's exclusive OR. So we use the exclusive OR here, exclusive OR, to toggle. If it's all at the beginning, it's even frequency, right? Because it appears 0 times. We have one element coming, it becomes odd, and the next element becomes even, odd, even, odd, even. We use this mask, okay? So we use the mask because each integer is basically a binary. So for example, 8-bit binary will be 8 bits, right? This is the binary. So each bit stores 2 states, 0 and 1. So we can use these, right? One shift position root of value to the left. So each one, for example, if value is 1, this is value 1, value 2, value 3, value 4, 5, 6, 7, etc. Okay? So we use these mapping, so to map each digit from 1 to 9 to each bit in the binary. And depth first search on the left tree, on the right tree with the mask. If it's a leaf number, root of left equals root of right equals none. If it's a leaf node which doesn't have any kids, then we check, right? We check. So at the beginning, if it's all 0, then it means that all numbers appears even number of times. Then we can make a palindrome out of it, right? And if we want to find out if it's the only single one, right? So if there's only single one, it means that only one element appears a number of times. We can also make a palindrome out of it, right? We just put that element in the middle, okay? And then we increment the answer, return answer. So yeah, this answer, okay? Some people would like to put this answer and then here, self.answer instead of return 0, self.answer plus equal 1, and that's also fine. Okay? So depth search, right? Depth search, visiting the trees left as we can, and if we can't, we come back, we retreat, and then visit the right tree. Okay, this is the depth search. Okay, so for example, the depth search can have many traversal orders. If we go for the in order, so what's in order? In order is left node right. Okay, so what's the left node right? What's the in order of this binary?
3, 3, 1.
3, 3.
1,
Okay, so 3, 3, 1,
2, 1.
2, 1, 1. Yeah, is it?
Yeah.
So basically, left, we want to visit the left tree first, and then the node, and the right tree. So left tree, we can recursively, if for this subtree, we can visit the left tree, which is 3, and the node. Okay, so 3, 3, 1, and then 2. And for this one, we want to visit the left, which is nothing, and node 1, 1. Okay, so it's actually this order. 3, 3, 3, 1, 2, 1, 1. Okay. How about breadth search? What's the order of the breadth search here?
2, 3, 1, 3, 1, 1.
2, 3, 1. Yeah, just level by level. Okay, so we need one kind of data structure to implement a breadth search. What is it?
Key.
Double-ended queue. Yes, double-ended queue. So queue first in, first out, right? First in, first out. The first in, first out double-ended means that we can push and pop on both sides in O1 constant time. If we use the list, if you use the list in Python, that only guarantees O1 on the right-hand side. If we do something on the left-hand side, this is going to take ON. For example, like if it's a simple list, if we insert an element here, can you imagine, for example, this original element is 1, 2, 3, 4. If we want to insert another element here, then the rest element needs to squeeze one position to the right. That's going to take ON time, right? For example, if you go to a cinema and somebody is sitting here, and you found out that it's your seat. So what happened? So you need to ask this guy, very polite, very politely, you are on my seat. And he or she realized, okay, yes, I made a mistake. And all these people are making mistakes. They saw that they are on the right seat, but they are not. So this person stand up, move to the right. This person stand up, move to the right. Everybody shift one position to the right. Now, not very convenient. That's right. Yes, that's all.
Especially if you put a cushion there and then you forget to take that cushion.
So we use the double-ended queue. Sorry.
Like for example, if one person gets it wrong, doesn't mean that everyone else gets it
Okay,
wrong.
okay, that's right. Yes, my assumption is that everybody gets the sheets wrong. Okay. So we use the double-ended queue to achieve the O1 constant on the left-hand side as well. Okay. So how do we perform the breadth search? Let me remind you.
You could also put a chair in front, but then that would just look weird.
Okay, so let's take a look at these. Just label it with different numbers, please. 1, 2, 3, 4, 5, and then we have another 6, 7, 8. Okay. So for example, like level by level, 1, 2, 3, 4, 5, 6, 7, 8. So at the beginning, we put the root in the queue. 1. Have we got the element in the queue? Yes, we take it out. When we take the element out, we take it from the left hand side. We push the element in, we put it on the right hand side. Let's call the first in, first out. Yeah, just imagine you are waiting in the queue. The people on the front get served next. Okay, and when the newcomers join, they need to, wait in the queue behind, right? So 1, take it out. Okay, take it out. We visit this. What's the kit of 1? 2 and 3, right? 2 and 3. We put the left in, and we put the right in. 2, 3. What's the next to take out? 2, right? What's the kit of 2? 4 and 5, right? So put it at the back. In queue, this is called in queue. What's the next to take out? On the left, right? 3. What's the kid of 3? 6. Okay? What's the next to take out? 4. It doesn't have a kid, okay? So we continue. What's the next to take out? 5. What's the kid of 5? Nothing. Okay, what's the next to take out? 6. What's the kid of 6? 7 and 8. Okay, do you see this? Yeah, do you see this procedure? And then 7, 8. So you see the order we get is 1, 2, 3, 4, 5, 6, 7. Okay, this is called the breakfast
That's
search.
1, 2, 3, 4,
Okay.
8, 6.
5, 6. Okay, so now let's implement this. So why can we use the breakfast search? Because the order of traversal, the tree, binary tree, doesn't matter, right? Doesn't matter. Does it matter? As long as we keep a state for each node. For example, when we're visiting the node, we know the number of the values we collected from the root to current, right? So as long as we have that information, the order of traversal doesn't matter. We can do this pre-order, in order, reverse in order, the depth search as well. This one depth search, what order is this? We visit the left tree, we visit the right tree, and we visit the node, right? So basically, this is what order is this? Actually, look, we visit this node here, right? We visit this node here. So it's node left R. What's this order? I don't know. Node left R, right? Because look, recursion, we visit the node, we visit the left tree, we visit the right tree. But it doesn't matter. Why is that? Because the order of traversal, it doesn't matter. We can just swap these two, right? We can visit the right tree, we can visit the left tree. It still works. It doesn't matter actually, right? It doesn't matter on which order we traverse. So we can use the breakfast search to solve this problem. So let's write the breakfast search. What were you saying?
Do you even know what the orders apart from in order?
In order.
Because like
Basically, it's a permutation of these 3 letters.
I know, but do you know
But
the
are
other
there any other
names?
types?
Okay.
I know there's other types, but I'm asking if you know the names.
This is called pre-order. Actually, there's a trick to remember what order is it. You just
No.
look at the position of the list node. Okay, if it's on the first one, it's pre. If it's on the middle one, in. If it's on the last one, it's called post.
But what about the L and R? Because like
LR.
NLR.
Then you put the reverse it, for example.
No, NLR is different to NRL.
That's right. Okay, so this is pre-order, right?
Yeah.
So it's NRL. We call it reverse pre-order.
Yeah.
Okay.
So does it mean the L always have to come before the R?
No. I mean, this is a
So
separate
how are you
order.
supposed to know when to say reverse?
If it's reversed, you swap the
I know,
LR.
but how do you know it's reversed?
What do you mean? How do you know it's reversed?
Because
How do you know
Because
it's
you know
reversed?
you know normal is NLR,
Yeah.
but you don't know if the normal is NRL or N.
Okay, so give me a sequence and I tell you how to pronounce it.
Yeah, no, you don't get my
Okay, can you
question.
please say it again?
I said,
Yeah.
how do you know it's reversed and how do you know it's not reversed?
This is not reversed.
Yeah, how do you know?
L left right.
Yeah, that's what I said before. I was saying before that does the L have to come before the R, and you said no.
Because if you know, then that's reversed. This is
Yeah,
reversed.
no. I was saying for the normal version doesn't have the
Okay,
L become before the R, and you said no.
Okay, get it. It's just different ways of saying it. Okay, so let me write another one. So what's this? Okay, so what's this?
Reverse in order.
That's right, okay. And how about, what's this?
Reverse post order.
Yeah, you get it, right?
And
how
that's
about-
me. Eric's not saying it. Then.
Okay, what's this?
I'm gonna let Eric.
Post order.
That's right, yeah, you see, very simple. First thing to check where the
and
N
also
is.
you didn't say if it was post.
Okay, we check the position to determine is pre, in, or post. And we check
This
the
doesn't make
order
any
of
sense.
AR. And if it's a RL, then we add the post. Then the reverse. Otherwise,
But post
it's
doesn't make any sense.
post.
Yeah, it should be.
Poster.
It
Post.
should be stuff. It always.
Post means the behind, right?
No,
it
it
isn't.
should be called stuff order.
Okay.
So-
I don't know. Pre-post,
Order.
right? Pre, in,
Stuff
post.
isn't even. No, it should be
suffix.
No, it should be post suff because then suff is a.
Okay, never mind.
I guess people like that.
Order suff.
Okay, breakfast search, right? Breath.
Ah!
Not breakfast, okay? It's breath. Breath means
No,
the
I-
horizontal thing,
Yeah,
okay?
it's a D silent.
Okay.
It's a D silent.
Brett.
D?
Is it the D silent?
Brett.
You tell me, I don't know.
No.
I don't know actually.
Ding dong magoo.
Okay, so if the root is given nothing, we return 0, obviously, then we use the Q, right? Q equals PQ. We, at the beginning, we put the root in, which is a tuple, and then the root will be,
Oof.
at the beginning, we put a 0, okay? Then while Q,
Ryan, look at.
current, the mask equals Q dot pop left. We take it from the left hand side.
Isn't it funny?
Mask exclusive or equals root dot value, right? Current dot value actually. Current dot value.
Owie!
Okay, now we need to check, right? If the current
Owie!
if current is a leaf node, okay? If the leaf node, how do we check if it's a leaf node? We check if it doesn't have any kid, right? If leaf dot left
Why
equals
is
leaf
it
dot
even
right.
called kid?
Okay, and then we need to check if m
Ta-da! I got
n
smart
minus
one.
1 equal 0, then
No, no,
answer
face.
plus equal 1. Answer at the
My
beginning
face.
we set it to 0. Otherwise, if the current dot left, then we push the left key, which is q dot append. Append to the right hand side, we just append. Append current dot right, current dot left, and then mask.
Owie!
Then if current dot right, q dot append, current dot right, mask. Okay, and then return answer.
Owie!
Okay, can I repeat? Okay, let me explain this breakfast session a little bit. Okay, DQ, double DQ. At the beginning, we put the root node in. Together, we put the mask, right? This is why we have a tuple. This is a list. We put a node and a mask. Answer equals 0. We want to get it, count how many paths, palindrome paths, okay? While we have element in the queue, then we take it out from the left-hand side. Then we update the mask. Mask exclusive or actually there's a mistake. When I write the code, I didn't realize this is mistake here, right? Yeah.
That don't make no sense.
One shifted root of value minus 1. Okay. If it current is the leaf node, this is basically the same thing here, right?
It's an exclamation mark.
If root of left equals root of right equals none, it means that it doesn't have any kids, it's a leaf node. Then we need to check the mask. If it has at most, this means if it has at most one single one. It could be all 0, means all the elements appear 0 number of times, including those missing numbers. Or if there's only single one, means that that particular number appears odd number of times, then we have one more pass, which it can be palindrome. Then otherwise, we need to check if we have left kid, we push to the left kid. If not, if right kid, we push to the right kid. Okay, so what's your question?
I don't get how do you know that if it's from a root to a leaf.
That's very good. Okay, from root to the leaf. The second parameter. Okay, the second parameter. Remember, this is the single integer. Integer, binary, right? Each bit, right? This represents 1, 2, 4, 8. So each one we can say this bit is 1. Represent if it's even or odd for the digit 1. The second to the right is for the digit 2, 3, 4, 5, etc. So each one, the number of frequency for all the digit 1 to 9 can be represented using a single digit. And for the breakfast search level by level, right? We always update the mask. Exclusive all, right? So current digit is current of value. Then we update the mask, and we pass along the mask when we put the new element to the queue, right? Remember, to the queue. So this is breakfast search. Do you get it now? This is similar to the depth search. Depth search here, mask. We pass it down. We pass it down to the depth search left, depth search right. Okay. Similarly, here we use the queue. Okay. So this is breakfast search. As I said, the order of traverse of the tree doesn't matter. So we can change the DQ to stack, right? to stack, which is the list. Am I right? And it still works. So look, if we just use the list, and instead of pop left, we just use the pop. Okay, and it still works, right? Just can you imagine if we use the stack instead of queue? What order will it make? For example, the original tree, right? Look here, 1, 2, 3, 4, 5, 6, 7. Okay, so breadth-first search DQ we know is 1, 2, 3, 4, 5, 6, 7. It's level by level, right? One exercise. If I change this DQ to stack, what order can we get? Okay, stack is first in, last out. If we replace the queue with the stack, we get a different order. If we replace the queue with the stack, so for example, like if we get this 1, right? If we put a 1 and we push the kid, which is 2 and 3, okay? 2 and 3. So 2 and 3, okay? And the next kid to take out is 3, okay? And then what's the kid of 3? Which is 6, 7, no? 6, 7. And then the next one take out is 7, 6, 2, 5, 4. Okay, so this one is reverse preorder. But if we swap around the left and right node, if we push the right node first and then we push the left node next, then we get a different order, which is node left right, which is the preorder. Okay, so what have we just done? We just replaced the DQ. We replace the DQ with the stack, right? We replace the DQ with the stack. Instead of pop left, we just use the pop, and then we get a different traversal order. And in this case, the order to traverse the tree doesn't matter. We still solve this problem, okay? So, what have you learned today?
We learned nothing.
Preorder.
You learned nothing?
Yeah, we're just recapping that.
Yeah, so, okay, so let me sum up, okay?
Preorder.
Careful, Eric. So let me sum up. Okay, so on that day we talk about this problem and we are solving it using the depth search. Okay, depth search. And today we just solving this using the breadth search. And we also talk about the trying to replace the queue with the stack. We get the different traversal order, the preorder, reverse preorder. Okay, depending on how we push the queue to the stack. It depends on the order of left and right node, okay? So, okay, the key thing to solve this problem is using the mask because we only have 9 digits and we want to store the status, whether they appear even number of times or odd number of times. It's just binary, right? If it's odd or even, we can store it using a single digit because each single digit in binary, each bit can be 1 or 0. 0 means the even number of times, 1 means the odd number of times, and we use this mask. We use exclusive of. If we exclusive of 1, then you will toggle. 1 will become 0, 0 will become 1, and that fits perfectly this purpose because at the beginning, this is the even number of times, and we have seen 1 digit, it becomes odd number of times, and it will come another digit, then it becomes even number of times again. Okay, so that's the trick to solve this problem. Okay, that's it for today. Bye bye.
Preorder.
Bye bye. Bye bye. Bye bye.
Preorder.
Bye bye.